Hey there, ladies and gentlemen. I am going to go over the answers to the review sheet. If you don't have your purple packet out, and if you're not open to the review sheet, I don't know what you're doing, because that's what we're about to do. You also generally need a periodic table pretty much every time you're in chemistry, so you probably have one of those out as well. So nomenclature breaks apart into three categories: molecules, ionic compounds, and acids. We've been doing this for a couple days. Hopefully you already know this. Molecules are mixtures of just nonmetals. When we're doing the names, we use prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Ionic compounds are metals and nonmetals, and they use the charges. I threw this periodic table up here showing the common charges. If it's not in one of those columns, which I kind of have this weird thing here blocking bunch of stuff. If it's not in one of these columns, their charges change, and there's probably going to be Roman numerals. We'll see a couple of examples. And then acids are hydrogen followed by some sort of anion, like a negative ion. That's what anion means. And we use the little adic, ite, us, hydro, blankic to kind of figure out how to name it. And then, of course, since acids have a hydrogen and hydrogens are a +1, we end up having to balance the charge between the +1 and whatever the anion is with a couple of hydrogens. So I'm only going to do the ones that I put a purple box around. There's too many for me to go over every single one. Again, though, the first thing you want to do is identify which category it is. If it's a molecule, it's got nonmetals. If it's an ionic, it's a metal and a nonmetal. If it's an acid, well, actually, acids are very easy to identify with the names because they say things like acid. So if you can't identify the acids on the test, I don't know if I can help you, because they say acid in the name. That's why I'm saying it like that. So let's just knock this out real quick. We'll start with number 3. We'll go across the ones on the top. Number 3, we have potassium oxide. Potassium is K, oxygen is O. I go to the periodic table. Potassium is a +1, oxygen is a -2. And since oxygen needs to take 2 electrons, but potassium can only give away 1, it's going to take 2 potassiums for every 1 oxygen. 2 potassiums for every oxygen. That's why the answer was K2O. This ionic over here, number 22, ammonium phosphate. Both of those are polyatomic ions. Ammonium was NH4 +1. And phosphate is PO4 -3. I would put both of those in parentheses and then worry about how to deal with the charges. Since phosphate needs 3 electrons, 1 ammonium is not going to do it. 1 ammonium can only give it 1 electron, so it's going to take 3 ammoniums to satisfy the electron needs of 1 phosphate, which is why there are 3 ammoniums for every 1 phosphate. Number 6 is a molecule. I can tell it's a molecule because this is a nonmetal and chlorine is a nonmetal. I can also tell it's a molecule because they use the prefix tri, which means 3. There are no charges used in molecules. This is 1 phosphorus and 3 chlorines, and you're done. You move on. Let me scroll down. I'm going to try these 3 also. In number 13, copper is in that weird part of the periodic table. Copper is right here, and we don't know the charge of elements in that zone, so they had to tell us the charge in the name. And what did they tell us? They told us copper is a +1. They did that with that Roman numeral. So copper is a +1. Chromate is a polyatomic ion. You're supposed to know that one. CrO4 is a -2. It would take 2 coppers to make the chromate have enough electrons, because the copper can only give away 1 electron in this case. That's why this formula is Cu2CrO4. And then the last 2 examples I'm doing on this side are acids. This is sulfuric acid, while the other one was hydrosulfuric acid. And the little phrase we were using was ate-ic, ate-us, hydro, blankic. and generally the blank was filled in with whatever element was going along with the hydrogen. So scrolling down, 8-ic, 8-us, 8-ic, 8-us, not quite far enough. Here it is, sulfuric, so that's actually sulfate. So it's hydrogen and sulfate. Hydrogen's always a +1, sulfate's a -2, so it's going to take 2 hydrogens to balance out that sulfate. On number 38, we have hydrosulfuric. So that's hydrogen and the element sulfur. Remember, it was hydrogen fill in the blank with the element ic. So that's hydrogen and sulfur. And since sulfur is a -2 as an anion, as a negatively charged ion, it's going to take 2 hydrogens for every 1 sulfur. All of the other answers are also there, but they follow the same basic rules. For ionic compounds, you pull the charges off the periodic table and then balance them. For molecules, you use the prefixes, and that's it. And then for acids, you pull the charges based off of what the name is. So ics become eights, ites become us's, etc. On the back, we're having to reverse the process. I'm going to do the 6 I have a box around. So this is a metal and a polyatomic ion. You can always tell when there's a polyatomic ion because there's way too many elements. Like, look, there's 3 elements. One of them is a polyatomic. Too many elements must be a polyatomic. Too many elements must be a polyatomic. So CS is the element cesium. SO3 is a polyatomic. It's not a polyatomic ion you're supposed to know. So you can find that one on the back of your periodic table with the huge number of extra polyatomic ions that you don't need to have memorized. Number 48, we have iron and the polyatomic ion hydroxide. But, like we mentioned, the difference between this answer with cesium and this one with iron is their placement on the periodic table is very different. Let's go back to that periodic table I had. So cesium's in the +1 column. Cesium always a +1. Iron is actually here in this weird blob that kind of got caught up. But iron's in that area where they can change, and we don't know its charge. Its charge can vary pretty drastically, while cesium is always a +1. So when we give people the name, we need to tell the charge for iron by doing some deductive reasoning here. Whereas with cesium, cesium's always a +1. We would never say cesium +1 sulfite, because cesium's always a +1. That would be kind of silly. So let's figure out how I determined that Roman numeral. Obviously it's going to be a +3, but how did I figure it out? So let's write down everything we already knew. Alright, that's what we knew just from the question. And let's see what other numbers we can fill in. How many irons are right here in this formula? There's OH3, but there's only 1 iron. That's important to fill that in. OH is a polyatomic ion, and it is always a -1 charge. It never varies. That's one of those ones you had to memorize. We don't know this charge, though. So we're going to use some logic here. The hydroxides take 1 electron. There are 3 hydroxides. Each of them is taking 1 electron. So that's 1, 1, and 1 for a total of 3 electrons that were just taken. So there were 3 electrons taken by those hydroxides. There's only a single iron. These electrons come off of that iron. So that iron must be a +3 because it's giving away 3 electrons. So what we're indicating here is that iron is a +3 by putting a Roman numeral 3 in the name. Iron, giving away 3 electrons, hydroxide. Let's try that same idea with 52. I'll come back to the acids. I like to do one category the entire time before I switch. So let's just go down to 52 and then 56. Copper, also in that weird area of the periodic table. So we write down all of the information we know about copper and oxygen. There's 2 coppers, 1 oxygen. I go to the periodic table, and oxygen is in the -2 always, while copper is not a consistent charge. But I can come in and I can go ahead and fill in the charge for oxygen right here. So oxygen is a -2. It takes 2 electrons. There's only 1 oxygen in this formula. But there are 2 coppers. So what are the coppers giving away? Each copper is giving away 1 electron. 1 electron from 1 copper, another electron from another copper. We have copper with a +1 charge. So the copper was giving away 1 electron, but there are 2 coppers. That's where the 2 electrons are coming from that go to oxygen. Calcium bromide. Why is this answer just calcium bromide? Why not a Roman numeral, man? I don't understand. Well, if you go back to the periodic table, let's look at calcium and bromine spot. Calcium right here, it is always a +2. Bromine right here, always a -1. Calcium is never anything but a +2. Bromine's never anything but a -1. So since those 2 are set in stone, we don't have to tell anyone the charge. We just say you got calcium and bromine. We do see, look at that. That bromine is changing its ending. Those nonmetals often become ides, especially in ionic compounds and molecules. The bromine becomes bromide, oxygen, oxide, that sort of thing. So that covers our ionic compounds. We're using the names of the metals. We're changing nonmetals to IDE. If there's a polyatomic ion, did I pick a poly? Yeah, like this was OH, so that's hydroxide. Let's see if I have any other good ones there. This was a polyatomic ion, so I just wrote its name. Now let's hit the acids. Okay. We have hydrogen and tellurium. So our acid rule again was 8s are Ix, ites are OUS, hydro, put the element in the blank ic. So this is hydrogen and tellurium, just the element tellurium. So tellurium got put into the blank, hydrotelluric acid. Hydrotelluric. I have one more. I didn't pick another acid. You know what? I'm going to pick another acid. Let's pick an acid. Here we go. We have hydrogen and a big polyatomic ion. C2H3O2 is acetate. ATE. So acetate is going to become, we changed the ending from 8 to ic. So we dropped the ATE and made it IC, acetic acid. So that's what we do with our acids. We change 8s to Ix, ites to OUS, and then hydro fill in the blankic. And then 79, this is a molecule. How do I know it's a molecule? That's right, good job. They're both nonmetals. Bromine and fluorine are both on that nonmetal side. Look, they're both right here. Fluorine and bromine are both on the nonmetal side of the periodic table. So this makes our lives very easy. When they're both nonmetals and we have a molecule, we can just use the prefixes. So the prefix for 3 is tri, which is what I'm hoping you're going to do on this test. Yeah, I keep making the tri joke. I'm sorry. There were a lot of really hard polyatomic ions on the back of this. Remember, any of the weird polyatomic ions are on the back of your periodic table. Go to the back of your periodic table anytime you're stumped with what that polyatomic ion might be. There's only about 30 of them back there. There was accidentally one polyatomic ion here maybe you couldn't find. I know a couple of you are ambitious. You may have done every problem even though you didn't need to. So BrO4 perbromate's not on the back of your polyatomic ion sheet. Sorry, totally messed that up. I won't be doing that on the test. Alrighty, let's clear off our desks. You should be getting a test in just a second. After you finish part 1, turn it in for part 2 and keep on going.